Hello, welcome to Quantum Online Academy. This is your Dr. Nagaraju Pendam. We finished the mathematical methods of physics in app, right? Now we are going to start with the classical mechanics. Once we have to go to the classical mechanics, today I am going to the special theory of relativity. Why I choose the special theory of relativity? Because special theory of relativity is the question coming area. All the topics I will tell, but even though why I start with the special theory of relativity, once you come to know about the special theory of relativity, rest of the classical mechanics topics is very easy to understand. That is why I started with the special theory of relativity. Clear? So, please you have to choose this institute. This institute will help you to get the knowledge in the physics, to stand in front of your students, to crack the exams also, if you practice perfectly. All my whatever I am giving the knowledge, that knowledge you have to keep in your mind, that is enough for you. Clear? Now, once we have to see classical mechanics. In the system, two varieties of the mechanics are there, one classical, another one is the quantum, right. Quantum, that advanced part is there, is statistical mechanics also, it will come some part of the quantum only, right. Bosons and fermions, those things will come onto the quantum mechanical concepts only. Now, once you have to see what is the classical mechanics through your naked eye, what are the things we able to see, those things we are describing in our physics language, that physics we call it as a classical mechanics. Among the classical mechanics, we are going to discuss about the theory of relativity or special theory. Their theory of relativity. What is the theory of relativity? Once you have to see the theory of relativity means, first you have to see the definition. Why I am writing the definition now? After completion of this topic, I have to make it is a PDF and I will upload in our app. To write this all these things, it is very easy to you. That is why I am taking the writing, that is very important, because once I tell no, immediately it will go off, you unable to make the notes. To make the notes purpose of you, I am writing each and every one also, please do not mind. Now, you have to see theory of relativity. What is the theory of relativity? Relativity means there is a relation. Relation between whom and whom? The relation between motion of the particle and the rest particle. So, there is a relation between the motion of the particle and the rest particle. That theory we call it as a theory of relativity. Once you have to see the theory which deals with the relativity of motion, the theory which deals with whom? The deals with the relativity of motion, the theory which deals with the relativity of motion, and the rest is called theory of relativity. The theory to whom? The theory which deals with the relativity of motion and the rest we call it as a theory of relativity. Clear? This theory of relativity is two types. The theory of relativity is two types. One is, once you have to see the theory of relativity is divided into two types. One is which one? That is a special theory. First one is the special theory. Which theory it is? Special theory. The second one is a general theory. The second one is the general theory. The first one is the special theory. The second one is the general theory. What is the special theory? It deals with objects. It deals with objects and systems. It deals with objects and systems which are either moving at a constant speed with respect to one another or at rest. We call it as a special theory. It deals with the object and systems which are either moving at a constant speed with respect to one another or at rest. We call it as a special theory. So these one who able to perform inertial frames. So those inertial frames are going to discuss in the special theory. What is the general theory? It deals with object and systems. It is also deals with objects and systems with are speeding up and slowing down. The speeding up and slowing down with respect to another, that theory we call it as a general theory. Where we are discussing this general theory, we are discussing with the general theory in non-inertial frames. Where we are discussing with general theory in non-inertial frames, we are discussing with the general theory. This is very very important. What is the theory of relativity? So it deals with what? It deals with the relativity of motion and rest. We call it as a theory of relativity. We are dealing with the relativity of motion and rest. We call it as a theory of relativity. This theory of relativity is two types. One is the special theory, another one is the general theory. What is the special theory? It deals with object and systems which are either moving at a constant speed or at rest, either moving at a constant speed or rest. Such type of theory we call it as a special theory. What is the general theory? It deals with object and systems which are speeding up and slowing down, with respect to another. Such theory we call it as a theory of general theory, right? Here special theory, who execute the special theory, inertial frames execute the special theory and non-inertial frames are execute the general theory. The special theory of relativity was proposed by Albert Einstein in 1905, because years also they are asking, so please remember the years, because TSPSC asked in Polytechnic 2023 examination 13 questions they are asking based on the years of the chronological theories. So that's why you able to remember which theory when come, after the theory who invented. So these chronological order also you have to remember. Competitive people, any question they will make it. We are not comment why people are making such type of a question. We are unable to comment. You come to know that one also. That is the thing. So that's why I am giving the years also. The special theory of relativity was proposed by Albert Einstein in 1905. The special theory of relativity was proposed by, who proposed this one? Albert Einstein. When he proposed 1905, he proposed that one. Clear? This is the theory of relativity. Theory of relativity is two types. One is the special theory, another one is the general theory. What is the special theory? Object and systems are with constant motion or rest. This theory we call it as a special theory. What is the general theory? Object and systems are speeding up and slowing down with respect to another. We call it as a general theory. Here you have to see in the special theory, we call it as a inertial frames can execute the special theory, non-inertial frames can execute the general theory. Special theory of relativity, who invented the special theory of relativity? Albert Einstein invented the special theory of relativity. Now frame of reference. What is the frame of reference? You have to see, right? One reference frame we have to keep. Any system relative to which the motion of an object, any system relative to which the motion of an object can be described is called a frame of reference. So what is the frame of reference? Any system you have to take, any system relative to which the motion of an object, any system relative to which the motion of an object can be described is called frame of reference. Any system relative to which the motion of an object can be described is called the frame of reference. So how many frame of references are there? Majorly two frames of references are there. one is types of frame of reference. One is inertial frames, we also call it as a unaccelerated frames. Inertial frames, we also call it as this frame, we also call it as which frame it is? Unaccelerated frame. This one is non-inertial frame or accelerated frames. Non-inertial frame or accelerated frames. Once you have to see what is the inertial frame. When bodies in this frame obeys, Newton's laws of motion, Newton's laws of inertia. When bodies in this frame obeys Newton's laws of inertia, means this is the first law of the Newton. First law of Newton. First law of the Newton. First law of the Newton. So, when bodies in this motion, in this frame of reference, obeys the Newton's law of inertia and other laws also. Other laws means second law of the Newton, second law and third law. Second law and third law also. And other laws of the Newton mechanics. Such type of frame we call it as a inertial frame or unaccelerated frame. What is the inertial frame or unaccelerated frame? When bodies in this frame obeys Newton's law of inertia and other laws of Newton mechanics, we call it as a inertial or unaccelerated frames. Now I am coming into the non-inertial or accelerated frame. This is the completely reverse. In this frame of reference, Newton laws are not valid. In this frame of reference, Newton laws are not valid. Such frame of reference we call it as a non-inertial or accelerated frame of reference. When a body acted upon by acting external force, we call it as a accelerated frame. So this one also I will give in the next slide also. Once you have to see the frame of reference. First what we have to tell. So the frame of references are two types. One is inertial frame of reference or unaccelerated frame, non-inertial frame, accelerated or rotational frame of reference. These three names are there. What is these three names? The first name is non-inertial frame of reference or accelerated frame of reference or rotational frame of reference also. So these three names are there. Here you have to see inertial frames or unaccelerated frames. Only two names are there. Inertial frames or unaccelerated frames. Types of frame of reference. In a types of frame of reference, the first reference is inertia or unaccelerated. Here non-inertia, accelerated or rotational frame of reference is there. Clear? Now once again you have to see, when bodies in this frame obeys the Newton's law of inertia and other laws of the Newton mechanics, we call it as a inertial frame or unaccelerated frame. First, when bodies in this frame of reference, Newton laws are not valid. Newton laws are not valid. Such one we call it as a non-inertial frame or accelerated frame or rotational frame of reference. Clear? Now here you have to see a body not acted upon by any external force is at rest or moving with a constant velocity. It is nothing but a kinematics theory. A body not acted upon by any force. Suppose you have to take a body not acted upon by any force, such type of the constant speed or rest in that body, such type of motion we call it as a inertial frame or unaccelerated frame. Clear? So now you have to see, when a body acted upon by external force, we call it as a accelerated frame. What are the examples? Once you have to see examples of the unaccelerated, examples of a accelerated frame of reference. Earth is inertial frame of reference. You have to take Earth is a inertial frame of reference. The second example is the law of physics will be same for all observers. The law of physics will be same for all observers. In the laboratory, you have to take the laboratory observation you have to consider as a frame of reference. Which frame of reference? Inertial frame of reference you have to consider. Now you have to see Coriolis force. Coriolis force is a non-inertial or rotational or accelerated frame of reference. Centrifugal and centripetal forces are centrifugal and centripetal forces are these rotational frame of reference or non-inertial frame of reference. These are the types of frame of reference. How many types of frame of references are there? Two types of frame of references are there. One is inertia or unaccelerated, other one is non-inertial or accelerated frame of reference. Clear? Now we will see if earth is inertial frame of reference or non-inertial frame of reference. Suppose you have to take earth, you have to consider earth we consider as a inertial frame of reference. In previous slide we shown example of the inertial frame of reference. I have to take it as a earth. Earth is the inertial frame of reference. The physics of all the laws according to the observer, that is also you have to consider as a inertial frame of reference. Suppose you have to see is earth is inertial frame of reference or not. How we have to explain? If earth is inertial frame of reference or not, how we have to explain? Suppose you have to see the first one, how we have to explain once you have to see here. Suppose here sun is there in a sun solar system, sun earth solar system, right? Sun is in this, you have to consider. Now you have to see this one is the earth. Which one you have to take? It is earth. Clear? Earth is there. Now around the sun, earth is revolving with velocity v is equal to r omega. V is equal to r omega with velocity. How velocity? V is equal to r omega, it is revolving. Now you have to see from sun to earth there is a distance is there. The distance we call it as a r distance. Clear? First we have to see. According to the sun earth motion, earth is revolving around the sun with v is equal to r omega. Right? What is the distance between the sun and earth? The distance between the sun and earth is equal to r. Now you have to observe the radial acceleration. What is the radial acceleration formula? The radial acceleration is equal to which acceleration? Radial acceleration. The radial acceleration AR is equal to A suffix R is equal to V square by R. This is the radial acceleration. V square by R. This is the formula for the radial acceleration. Therefore, A suffix R is equal to V is equal to R omega. R omega whole square is divided by R. So, therefore, R square omega square is divided by R. 1 R get cancelled. R omega square it will come. R omega square. What is the R? The distance between the sun and earth. What is omega? Omega is equal to which one we have to write? This is the angular frequency. Omega is equal to 2 phi by t. Omega is equal to 2 phi by t. So, here t is equal to what is the t? The earth to complete the rotation of the sun, it will take 1 year. You have to write it is 1 year or 365 days. 365 days if you have to see. Then you substitute there angular acceleration you have to find. Therefore, the angular acceleration how much you are getting? 0.006. So, what is the acceleration unit? Meter per second square. You will get 0.006 meter per second square. You have to get it. Clear? 0.006 meter per second square we are getting through the sun earth motion. The acceleration of the sun is the acceleration of the earth is 0.006 meter per second square. The same thing if I have to consider I have to consider the second one you have to see. Second one you have to see, only you have to consider the earth. What is this earth? This one is you have to consider as the earth, right? Now on the surface of the earth, one person is sitting. One person is sitting on the surface of the earth. One person is sitting. Clear? On the surface of the earth, one person is sitting. What is the radius of the earth? The radius of the earth is equal to capital R. Now earth is revolving around its own axis. So that's why this person also revolving. V is equal to R omega. So V is equal to R omega. Clear? So what is the radial acceleration of this person? Once you have to see the radial acceleration. Radial acceleration. The radial acceleration of whom? The radial acceleration of the surface of the earth person is equal to V square by R. But here V is equal to what we have to write? A suffix R is equal to R omega. Which R it here you have to take here. Here also you have to consider as a R. So V square by R, R omega whole square is divided by R. Here R square omega square is divided by R get cancelled. Therefore, the angular acceleration AR is equal to R omega square. This is the angular acceleration. Now you know what is the omega. Omega is the angular frequency. Omega is equal to 2 pi by t. But around the earth, so to rotate the earth, t is equal to how much time it will take? It is 1 day. 1 day is equal to 24 hours. 1 day is equal to how many hours you have to take? You consider as a 24 hours you have to consider. How many hours you have to consider? So 24 hours you have to consider. So if you consider the 24 hours, you calculate the omega and substituted there. R is equal to, R is the radius of the earth. So radius of the earth is 6 kilometers. You have to substitute. Therefore, you will get the angular acceleration. How much angular acceleration you have to get? 0.034 meter per second square we are getting. Once you have to see, earth is revolving around the sun, you are getting the angular acceleration is equal to 0.006 meter per second square. Earth is revolving its own axis. Therefore, the angular acceleration of the surface of the person is equal to 0.034 meter square. Suppose if you have to take, how we have to correct it? Suppose on the earth, maybe this is the earth is there. Clear, you have to take the third one you have to see. On earth is there, right? On earth is there. Around the earth you have to cut it like this, right? You cut it this. On the axis of the earth, one person is sitting. On the axis of the earth, one person is sitting, right? Is moving on the surface of the earth 100 meter per second. Is moving with 100 meter per second velocity is moving. Clear? So now, so initially you don't have any velocity because of the earth is moving with 100 meter per second, that is the final velocity v. Therefore, we have to take it as a correction we have to do. How corrected this one you have to see, right? So, the distance delta x is equal to, according to the kinematics relation, 1 by 2 of a t square, 1 by 2 of a t square, right? Delta x is equal, because u is equal to 0. Final velocity is 100 meter per second square velocity is there. So that's why the initial velocity u is rest, that's why it is 0, because the person is rest initially, and after some time is moving with velocity 100 meter per second square. So therefore delta x is equal to, there is a correction, delta x is equal to, so 1 by 2 into a is equal to, what is the radial acceleration of earth? The radial acceleration of the earth, now only we found 0.034 meter per second, and t is equal to, you have to consider as a, in 1 second you have to consider. So therefore delta x is equal to how much we are getting? 0.017 meter we are getting, 0.017 meter we are getting. Therefore, so what we have to write? Our x is equal to what we have to write here? 100 meter per second, 100 meter distance is there, or 100 meter. So plus or minus what we have to take? 0.017 meter, plus or minus 0.017 meter. This is the distance we have to calculate. So like this we have to do the correction, right? We have to do the correction. So therefore, in practical purpose, S is not inertial frame of reference, because if it is inertial frame of reference is execute, this law can possess in wherever you go, the same value you will get it, because here we are not getting the same value, but in practical purpose earth can take as a non-inertial frame of, theoretically non-inertial frame of reference only, but even though in all practical purpose, but even so all practical purpose, but all practical purpose earth can taken as a inertial frame of reference, earth can taken as a inertial frame of reference. Clear? For all practical purpose we have to take, for all practical purpose earth can take as a inertial frame of reference, but theoretically earth cannot be inertial frame of reference, because angular acceleration is varying, it is accelerating frame. So that's why it is non-inertial in theoretical, but in practical purpose we are considering as a earth can take as a inertial frame of reference. Clear? Now we will see with another topic. So that is the Newtonian mechanics. Maybe we have to start the classical mechanics with Newton laws only according to your syllabus, but the Newton laws is very boring. So you come to know from the 6th class onwards Newton laws are there. So that's why I decided to teach with the special theory of relativity. After finishing the special theory of relativity, again I am coming into the Newton laws. First you have to see the what is the introduction about the Newton mechanics or Newtonian mechanics. This Newton 16th or 1600 and which year it is there, the Newton is invented, so that year we call it as a the 16th century people. He invented 16th century 16th century person. Newton is the 16th century person. He wrote one good mathematical physics book one he wrote. There he discovered the 3 theories. Those 3 theories is Newton laws. Newton the first law, law of inertia; Newton the second law, law of motion; Newton the third law, law of reflection. Like this he discussed. So now you are able to see Newtonian mechanics is belongs to the 16th century. Before the Newtonian mechanics also some theories came, not is Newton first one, right? Please remember. Newtonian mechanics to explain the natural phenomena. Already I told, whatever the things we are able to see with our human naked eye, those things we have to simply describe by using the classical mechanics, those classical mechanics based on Newton principles only. Clear? So that is the thing. Newtonian mechanics invented in 16th century to explain the natural phenomena in assumptions. Based on what assumption? Any theory if we want to give, maybe that is the psychological theory or philosophical theory or political theory or any theory they want to make, first they will keep the assumptions, they will keep the predictions, they will keep the hypothesis. Maybe that hypothesis may be true or may not be true, correct? May be true or may not be true. So, those assumptions we call it as a hypothesis or assumptions. What is the assumptions? Once you have to see, space and time is absolute, space and time is absolute, space and time are independent of each other. Based on these two assumptions, Newton made one mechanics, that mechanics we call it as a Newtonian mechanics, clear? So, without assumptions, without the hypothesis, without the prediction ideas, we unable to do anything. Suppose if you want to crack the CSR exam, that is your hypothetical idea. Maybe if you do the hard work, right, whatever the practicing questions are there, those questions will come in your examination, you are able to crack. Otherwise, you unable to crack. This hypothetical idea based on your hard work, based on your practice, based on your remembering, based on your recognizing skills, you able to do in your examination. Otherwise, you unable to do. Clear? The same thing, one theory, how it will come? Based on the assumptions only. What are the assumptions? Space and time is absolute and space and time are independent of each other. Space and time is absolute. The first assumption is space and time is absolute. The second assumption is space and time are independent of each other. Those are the assumptions. Based on this, so this is very important. One note I am giving, maybe I have to teach after some time these things, how it is conserved, all these things we have to discuss while I am teaching the Newtonian mechanics. Once you have to see, whose space is homogeneous, whose space is homogeneous, whose space is homogeneous, which parameter is conserved? Linear momentum is conserved. Whose space is homogeneous, linear momentum is conserved. Whose space is isotopic, whose space is isotopic, which parameter is conserved? Angular momentum is conserved, angular momentum is conserved. Whose time is homogeneous, whose time is homogeneous, which one is conserved? Energy is conserved. So, maybe they are asking the question in CSIR for 3.5 marks. For 3.5 marks they are asking this question, whose time is homogeneous, which parameter is conserved? Which parameter is conserved? Energy is conserved. Whose time is homogeneous, energy is conserved. Whose space is homogeneous, linear momentum is conserved. Whose space is isotopic, angular momentum is conserved. So, these conservation principles will come in Newtonian mechanics. There I will teach to you, but here you have to learn. All three also very important. So, many times your competitive people are asking the question, whose space is homogeneous, linear momentum is conserved, whose space is isotopic, angular momentum is conserved, whose time is homogeneous, energy is conserved. So, this is very important. What is the homogeneous, what is the isotopic? I will teach you in the Newton mechanics, in Newtonian mechanics, in the Newton laws. This is the Newton mechanics. Now, after the we have to learn the Newton mechanics. Why we have to learn the Newton mechanics? Newton mechanics is execute the space and time are absolute and space and time are independent of each other. We are taking that assumption. Similarly, same assumptions it took. So, which one we have to do? Galilean transformation. Galileo Galilei is the before the Newton only. Galilean, he introduced the transformations. Those transformations we call it as a Galilean transformation. These transformations also call it as a Newtonian transformations. These Galilean transformation we also call it as a Newtonian transformation. Any theory, already I told, any theory we are keeping based on the some hypothetical idea. So, what is that hypothetical idea about the Galilean transformation or Newtonian transformation? The hypothetical idea is, here once you have to see, space is absolute. What is that? Space is absolute. Space is absolute is Galilean transformation hypothetical idea. Or time is absolute, space is absolute, or time is absolute. Both are absolute. This is very important. Please remember what is the Galilean transformation assumptions based on these two things. One is space is absolute and time is absolute. That's why these transformations we call it as a Newtonian transformation also. Why? Because Newtonian mechanics also based on these two assumptions only. Space is absolute and time is absolute only. The Galilean transformations are used to transform the coordinates of position and time. The Galilean transformations are used to transform the coordinates of position and time from one frame to another frame, from one inertial frame to another inertial frame. How we have to transform? Once you have to see. I will explain from one inertial frame to another inertial frame. How we have to get? Once you have to see here. Suppose if you have to take a two frame of references, you have to take, maybe this is the S frame you have to consider. This frame you have to take it as a S frame. Now this frame is a S dash frame. Which frame is S dash frame? This S dash frame is moving with velocity v. S dash frame is moving with velocity v. Now one person is simply sitting at particular point P. At particular point P is observing. Maybe you have to see is the observer, right? So is observing S frame things and S dash frame things is observing. So what are these coordinates? X comma y comma z comma t, x comma y comma z comma t, along with respect to whom? With respect to S frame. With respect to S frame, he observed x comma y comma z comma t. He observed with that one. According to the S dash frame, the same moment he observed x dash y dash z dash comma t dash with respect to whom? With respect to S dash frame. With respect to S dash frame, he is observing x dash y dash z dash t dash. With respect to S frame, his coordinates are x comma y comma z comma t. Clear? Now you have to see here. From here to, so there is a point is here, you have to take. From here to here, how much distance is there? The distance we call it as a v into t. From here to here, so you have to take the distance. So what is the distance you have to take? The distance is x distance compared to this to this S frame. There is x distance is there because it is a x axis. You have to take which axis it is? This axis is x axis. Clear? Now from here to here, from here to here, what is the distance? X dash distance is there. So therefore, based on the diagram, what we have to write? From the figure, once you have to see, from the figure, we have to write, what we have to write? X is equal to x dash plus Vt. X is equal to x dash plus Vt. Therefore, x dash is equal to x minus Vt. Y dash is equal to y. Z dash is equal to z. T dash is equal to t. So these equations we call it as a, which equations? Galilean transformations. Galilean transformations. These equations we call it as a Galilean transformations. Or these equations we also call it as, which transformation it is? Newtonian transformations. Newtonian transformation. Because why? Because we are using the same space and time are absolute. Based on that we have to write. Now you have to reverse it. So what will happen? You have to see. If you have to reverse these things, we have to take it as our Galilean transformations are, once you have to see our Galilean transformations. Galilean transformations. What are our Galilean transformation? X dash is equal to x minus Vt, y dash is equal to y, z dash is equal to z, t dash is equal to t, our Galilean transformation. Now you have to take the inverse of this, inverse Galilean transformation. How we have to write the inverse Galilean transformation? Here we have to take corresponding to the S frame, we are observing the S dash frame, that's why we have to write X dash. Now you have to see corresponding to the S dash frame, you have to observe the S, so you will get the inverse Galilean transformation. Galilean transformations. Inverse Galilean transformations are, what are those inverse Galilean transformation? X is equal to x dash plus Vt, y is equal to y dash, z is equal to z dash, t is equal to t dash. So these expressions we call it as a, which one it is? Inverse Galilean transformation or inverse Newtonian transformation we are taking. Why we have to take? Here we have to consider through S dash we are comparing the S. Now you have to take S, you have to compare the S dash, then you write the equation. Therefore you are getting x is equal to x dash minus Vt only you are getting. Clear? So that is the thing. Now based on these expressions we have to write for velocity component, how we have to write. For velocity component, how we have to write? So we know one thing, we know x dash is equal to x minus Vt, this is the position coordinate we have to write, right? You have to differentiate this, dx dash is divided by dt is equal to dx by dt minus, so v is the constant you have to take here, so v into dt by dt, so dt get cancelled. Therefore dx by dt is equal to u dash minus u minus v, u dash is equal to u minus v we have to write. So therefore how we have to write? Corresponding to the x axis you have to write u dash x is equal to ux minus v, because v is the constant here. For velocity components what we have to write? Therefore velocity is which one we have to write here? Velocity is variant. Therefore velocity ux dash ux is not getting, ux minus v we are getting. So that's why we have to take, according to the Galilean transformation, velocity is variant. The basic laws of physics are unchanged in two reference frames connected by Galilean transformation. The basic laws of physics are not unchanged, The basic laws of physics are unchanged in two reference frames connected by the Galilean transformation. This note you have to remember. The basic laws of physics are unchanged. In two reference frames connected by the Galilean transformation. That is very, very important. Clear? Now one more thing, for acceleration we have to see. What is the acceleration? Suppose you come to know u dash is equal to u minus v, correct? V is the constant here. Again you have to differentiate d by dt of u dash is equal to du by dt minus, so this is the constant value, how to take the 0. So therefore this a dash is equal to, the rate of change of velocity is the acceleration, a we are getting. The a dash is equal to a dash is equal to a, what we have to write? In terms of the ax dash is equal to a we have to get. So therefore what we have to write here? Acceleration is invariant. Acceleration is invariant under the Galilean transformation. Therefore what we have to write? Acceleration is invariant under the Galilean transformation, because one frame of reference we are getting a same acceleration in another frame of reference also. That's why acceleration is invariant. All the inertial frames, a body will be observed to have same acceleration. What we have to write here? So, the all the inertial frame, a body will observe to have the same acceleration. This statement also you have to remember, because theoretical questions they will make it. Now, Galilean invariance we have to see. How we have to see the Galilean invariance? Here two frame of reference is there. One frame of reference we have to take, that is the S frame of reference. One rod you have to take, that rod length is L0 length you have to take in S frame of reference. So, this one you have to consider as a x1 distance, and this is the x2 end points of this. This distance is L0 is equal to x2 minus x1. L0 is equal to x2 minus x1. Now, another frame of reference you have to consider. This is the S dash frame. The same length of the rod you have to consider. That length is equal to L. So, now the person is sitting here. So, he is observing this L dash L length corresponding to this. This one is the x1 dash, this one is the x2 dash, but L is equal to x2 dash minus x1 dash is there. L is equal to, right? Now, you have to see, if a rod has a length L0 in the frame S with the end coordinates x1 and x2, then the length is equal to x2 minus x1. If at the same time, the end coordinates of the rod S dash are x1 dash and x2 dash, x1 dash and x2 dash, then the length L is equal to x2 dash minus x2 dash. According to the Galilean transformation, L is equal to what we have to write here? L is equal to x2 dash minus x1 dash. But according to the Galilean transformation, x2 dash is equal to x2 minus Vt, minus of x1 minus Vt. We have to write x1 dash is equal to x2 dash is equal to x2 minus Vt, x1 dash is equal to x1 minus Vt. Therefore, what we have to take? X2 minus Vt minus x1, minus into minus plus Vt, minus Vt plus Vt get cancelled, x2 minus x1 we are getting, which is equal to length L is equal to. Therefore, L is equal to x2 minus x1. From this, what we have to write? We are getting the length is similar. So, in S frame we are getting the length L0 is equal to x2 minus x1. In S dash frame also we are getting the same length. What is that length? x2 minus x1. Therefore, similarly the length or distance between 2 points is the same. That is why what we have to write? Length is, therefore, length is invariant. Therefore, length is invariant. Which one we have to write here? Therefore, length is invariant. From this, not only length or distance between 2 points or mass, second one is the mass, third one is the time, fourth one is acceleration, before we discussed the acceleration, the fifth one is the forces, are invariant under the Galilean transformation. The law of conservation of momentum is invariant. The law of conservation of momentum is invariant under the Galilean transformation. So, please remember this statement also. But momentum is variant, but law of conservation of momentum is invariant under the Galilean transformation. Clear? So, this is the invariance, Galilean invariance. Now, what are the shortcomings of the Galilean transformation? Galilean transformation is not fulfilled in all the ways. So, first shortcoming is, first drawback. What is the first drawback? Suppose if you discuss no, what is the first drawback? You have to take the position, if you have to observe, position or distance you have to observe, position you have to observe. So, x dash is equal to x minus Vt. So, therefore, you have to find V dash is equal to U dash is equal to U minus V we are getting. because velocity is invariant, velocity is variant under the Galilean transformation. Velocity is variant under the, therefore what we have to write, velocity is variant under the Galilean transformation. Velocity is variant, this is the first drawback of the Galilean transformation. We are unable to express velocity is invariant, velocity is variant under the Galilean transformation. Clear? Now you have to see the second shortcoming is, what is the second drawback? The second drawback is very important. Suppose you have to see from the Maxwell equations in electrodynamics, Maxwell equations in electrodynamics, Maxwell equations, which one we have to write? Maxwell equations in where? Electrodynamics, electrodynamics, Maxwell equations in electrodynamics you have to observe. How many Maxwell equations are there? 4 Maxwell equations are there in thermodynamics, 4 Maxwell equations are there in electrodynamics, but these equations are not equal to that equations, those equations are not equal to this equation. Clear? Now we are discussing about the second drawback of what? Galilean transformation. First we have to observe from what is the Maxwell equation. So the first Maxwell equation is electrostatic equation, that is del dot E is equal to rho by epsilon naught. This is the del dot E is equal to rho by epsilon naught. This is the Gauss law. The second Maxwell equation is del dot B is equal to 0. The third Maxwell equation is del cross E is equal to minus dou B by dou T. The fourth Maxwell equation is del cross B is equal to what we have to write is mu naught J plus mu naught epsilon naught into dou E by dou T, mu naught epsilon naught into dou E by dou T. This is the this one is what one it is? This one is a modified Ampere's law. These are the 4 Maxwell equations are there. In electrodynamics, these 4 Maxwell equations are there. The first Maxwell equation is del dot E is equal to rho by epsilon naught, del dot B is equal to 0, del cross E is equal to minus dou B by dou T, del cross B is equal to mu naught J plus mu naught epsilon naught into dou E by dou T. Under the Galilean transformation, how we have to write this one you have to see. Under the Galilean transformation, what we have to observe? First we have to observe about the argument in 3-dimensional, under the Galilean transformation in 3-dimensional argument you have to take. Suppose what is that argument you have to see? R dash is equal to R minus Vt. This is the 3-dimensional Galilean transformation, right? R dash is equal to R minus T. T dash is equal to T. T dash is equal to T we have to write. So therefore, if you have to solve these Maxwell equations, you are getting that electric field E r comma T is equal to E naught into e to the power of I k dot r minus omega t, Similarly, B r comma t is equal to B naught into e to the power of I k dot r minus omega t, right? Suppose if you have to take the Maxwell equation, right, the solution of the Maxwell equation you are getting the E and B only. E is equal to E naught e to the power of I k dot r minus omega t. B is equal to, so r comma t B naught e to the power of I k dot r minus omega t, correct? So now you have to observe the, which one you have to observe? First argument you have to observe. argument you have to observe. That argument is equal to k dot r minus omega t, k dot r minus omega t in S frame. In which frame it is? S frame. You have to take this k dot r minus omega t in S frame. The same, so what is this argument? This argument will give the shape of the wave. Shape of the wave it will give. In electrodynamics, that is the wave nature is there. So that shape of the wave it will give k dot r. Now S dash you have to observe. S dash frame you have to observe. K into r dash minus omega into t dash. K into r dash is equal to, you have to substitute r minus Vt minus omega into t, t dash is equal to t, k dot r minus k into v into t minus omega into t. So k into r, k into v is equal to omega, omega into t minus omega into t we are getting, omega into t minus omega into t, minus 2 omega into t. So kV into t, so right you have to take it as a omega into t. In S frame, once you have to see in S frame, what is the argument? That argument is equal to, in S frame that argument is equal to k dot r minus omega into t. In S dash frame, that argument is equal to, what is that argument? S dash frame, once you have to see kr minus 2 omega into t, kr minus 2 omega into t, this is the argument. So therefore once you have to observe, in S frame argument is not equal to, in S dash frame argument is not equal to, in S dash frame argument, S frame argument is not equal to S dash frame argument, correct? So because here S frame argument is not equal to S dash frame argument, therefore what we have to write? Under the Galilean transformation, the Maxwell equations change their shape. Argument means there is a shape of the wave. Change their shape in transition from one frame to another frame. In transition from one frame to another frame, this is the second drawback of the Galilean transformation. Under the Galilean transformation, Maxwell equations change their shape in transition from one frame to another frame. The Galilean transformation is valid for mechanics but not in electrodynamics. From this, what statement we made? The Galilean transformation, from the Galilean transformation valid only for mechanics, not for the electrodynamics. To get the electrodynamics, we are going to discuss one more frame of reference. So one more transformation equations. Those transformation equations are low range transformation equation. Maybe tomorrow's class we have to discuss about the low range transformation equations. Clear? Now we will see what is the absolute frame of reference. So some little bit things we have to learn. What is the absolute frame of reference is, the velocity of light will be exactly equal to 3 into 10 to the power of 8 meter per second and will be same in all the directions. That frame we call it as a absolute frame of reference. The velocity of light will be exactly equal to 3 into 10 to the power of 8 meter per second square and will be same in all the directions as the frame is at absolute frame of reference at the absolute rest. So based on this, so we have to going for discuss one experiment. That experiment is Michelson-Morley experiment. Michelson one scientist, Morley is another scientist. Michelson one scientist, Morley is another scientist. They gathered, they did one experiment in 1887. When they did the experiment? In 1887 they did experiment. They got the Nobel Prize also. Michelson got the Nobel Prize in 1908. is the first American person to get the Nobel Prize in physics field. To get the Nobel Prize in physics field in 1908, is the first American to get the Nobel Prize. First American to get the Nobel Prize. When he get the Nobel Prize? 1908. In 1908, he got the Nobel Prize. Michelson-Morley experiment, when they did 1887 they did. So what purpose they did? That is very, very important. Search for an absolute frame of reference. We discussed the absolute frame of reference. What is the absolute frame of reference? The velocity of light will be exactly equal to 3 into 10 to the power of 8 meter per second, will be same in all the directions of the frame, is at rest, absolute rest, right. So now search for absolute frame of reference. The space is filled with substance. That substance he has taken as a ether. The space is filled with one substance. He took majorly one substance. That substance is ether. Ether, what is the ether? Ether is a material, right. This ether material qualities are: ether is invisible, you unable to see with your naked eye. Ether is a massless. Ether is perfectly transparent. Ether is a perfectly transparent. Ether is a perfectly non-resistive. Ether is having high elasticity and low density is there. These many characteristics are there. Ether. What is the ether? Ether is one medium. So that medium is once you have to see the ether medium. So then ether is invisible. Ether is the massless. Ether is perfectly transparent. Ether is perfectly non-resistive. Ether is having highly elasticity. Low density is there. These are the qualities of the ether. This ether is filled within the space. He assumed that, because any theory, already I told, if we want to give any theory, we keep assumption. That assumptions are hypothetical ideas. This hypothetical idea may be true or may not be true. Clear? So now you have to see. Search for absolute frame of reference. The space is filled with substance. We call it as a ether. The ether is invisible, massless, perfectly transparent, perfectly non-resistive, having high elasticity and low density. That is the qualities of the ether. This ether concept is supported by to determine the absolute velocity of the earth with respect to the frame. What is that? This ether concept, once you have to see, this ether concept is supported to determine the absolute velocity of the earth with respect to the frame. Michelson and Morley carried out an experiment to determine this absolute velocity of the earth. Absolute velocity of the earth means velocity is the same wherever you go. So for that he considered the ether medium and he did one experiment along with the Morley. That experiment we call it as a interferometer experiment. That experiment we call it as a Michelson-Morley experiment. Which experiment it is? Michelson-Morley experiment. Once you have to see the experiment, first you have to take the source. Which one you have to take? This is the source. Clear? You take the source. From this source light is illuminating. Now you have to see, able to see from this source which one you have to consider? Light is illuminating. To get this light to make a render, you have to keep one convex lens. This is the convex lens. Which one it is? Convex lens, that is L. To make this light, all the particles are going to all the direction. To make it as a parallel beam, we have to keep one lens. That lens we call it as a, which lens it is? So that lens is the convex lens. After taking this ray to incident on the glass plate, this is semi-silvered glass plate, G1 you have to take here, glass plate G1. So one more glass plate also here is there, that is the another glass plate, the semi-silver glass plate G2 also you have to keep. Now, so this ray is incident in the semi-silvered glass plate and some portion of part should be reflected back, the some portion of part should be transmitted. this transmitted ray we are getting here, this transmitted ray. This reflected one is going to this side, another one is there G2, right, G2. Now you have to see this G2 also, your reflected beam, it is going back. Now you have to able to adjust, this will go to this side. So now some portion of part should be reflected and the transmitted one, so the reflected one is coming to this side. So these two rays, G1, one ray is coming to the G1, another ray is coming to the G2. So these two rays are interfere, their interference pattern can observe on the telescope. So that telescope you have to see here through your human eye. So that is the telescope. That interference pattern, the fringes will observe like this. This is the pattern of the vertical fringes you able to get. So these are the fringes, right. So these fringe width you have to able to find out these fringe width from the experiment by using the spectrometer. You have to observe the spectra and you have to calculate the fringe width also you have to calculate. Clear? So this is the brief introduction about the Michelson-Morley experiment. Already you discussed in your BSc first year mechanics and your BSc third semester in optics also you discussed this one. The 2 times in your BSc you learned. If you go to the MSc also you have to learn the Michelson interferometer. Wherever you go the theory is the same. Now once you have to see the theory, what we have to observe? The optical path difference. So the optical path difference of this, so what we have to write this optical path difference is the optical path difference L into V square by C square. This is the optical path difference of the beams. 2 interference patterns we are getting, there is a path difference is there because exactly they are not coming in the same path, that is why there is a difference is there. Due to the difference, optical path difference, what we have to write? L into V square by C square we have to write. If you have to use the source, that source wavelength is lambda, maybe you have to use the 5000 angstrom source you have to use. So that source wavelength is lambda is used, therefore that optical path difference, how we have to write? L into V square by C square into lambda, that lambda I am writing here. So L by lambda into V square by C square. If you have to use the, so which one you have to use? The source lambda if you have to use. If you have to turn into 90 degrees of that mirrors M1 and M2, there is a screws are there, you have to adjust it and you have to turn the mirrors. So these mirrors M1 and M2 you have to adjust in 90 degrees you have to adjust. So what will happen? So there is a optical path difference, one more optical path difference you have to get. So what is that optical path difference? L by lambda into V square by C square you are getting. So now the resultant path difference is, so this path difference deviation you have to write 2L by lambda into V square by C square. This is the resultant optical path difference is there. The number of fringes shifts, how many number of fringes is the shift, that number is equal to what we have to write. So that number of fringes shifts is equal to 2L. This is equivalent to the number of fringes shifts 2L by lambda into V square by C square. 2L by lambda into V square by C square is there. So now you have to substitute the values. Now you able to get the value, the number of fringes you have to substitute 2 into, so L, how many distance, what distance you have to keep, the distance you have to see 1 into 10 to the power of 3 centimeters, in terms of the centimeters I am keeping 10 to the power of C. The V is equal to, what is the velocity of that light, that velocity you have to 3 into 10 to the power of 6 linear velocity of the earth we have to take 3 into 10 to the power of 6 centimeters per second you have to take. Lambda is equal to 5000 angstroms, you have to take it as a 5 into 10 to the power of minus 5 centimeters. In terms of centimeters I am taking all these things, and C is the light velocity. What is that light velocity? You have to take the light velocity 3 into 10 to the power of 10 centimeters you have to take 3 into 10 to the power of 10 centimeters. Now you have to observe n is equal to the number of fringes, how many number of fringes the shifts, that is the 0.45 fringes it is shifts, 0.4 fringes is shifting. Clear? So, the 0.4 fringes is shifting. This is the calculated value. Which value it is? Calculated value. Calculated value. Now, we did the experiment. So, we did the experiment there. So, there is a shift we have to find, that shift is equal to 0.01, 0.01 fringes we are observing. The shift number of fringes, how many number of fringes they are shifting? 0.01, that is the small. Small means almost is negligible, almost absence. We have to take it as a almost absence. So, therefore, such type of result, so if it is a calculated, in practical we are getting 0.01, 0.01 fringes we are getting in practical. So, practical, this result we call it as not exactly same we are getting, this result we call it as a null result. This result we call it as, which result it is? Null result. So, null result, this result we call it as a null result or negative result. Negative result. This result we call it as a null result, negative result. Based on this Michelson-Morley negative result, we got so much of important things we learned. So, because of this experiment failed, but he got the Nobel Prize. So, he gave the theory to Einstein, Einstein successed, and he also got the Nobel Prize. Once you have to see, it is impossible to measure the speed of the earth relative to ether. It is impossible to measure the speed of the earth relative to ether. This is the first assumption is failed. So, that is why we have to write, it is impossible to measure the speed of the earth. Speed of the earth relative to ether. Relative to ether, this is the first concept. The concept of the fixed frame of reference cannot be checked by this experiment. Fixed frame of reference we are not checking by using this experiment. This is the second mistake. The null result of the experiment lead to the total rejection of the ether hypothesis. This is by doing this experiment we are confirming, we are giving the statement, the rejection of ether hypothesis. The rejection of ether hypothesis because of the null result of experiment, we are going to lead the statement, that statement is rejection of ether hypothesis. Clear? This is the third one. Based on this, which lead to the theory suggests that, what suggests that the speed of light in vacuum instead of ether, we are going to take the vacuum is the same in all frame of reference which are in uniform related to the motion. This is a great success story by using the Michelson-Morley experiment. Clear? Once again you have to see the four conclusions are there. It is impossible to measure the speed of the earth related to the ether. The concept of a fixed frame of reference cannot be checked by this experiment. The null result of the experiment lead to the total rejection of the ether hypothesis. This theory suggests that the speed of the light in vacuum is the same in all frame of reference which are in uniform related to the motion. Clear? So, this is the very great discovery in 1887 by using Michelson-Morley experiment. Now, I am giving some theories. You have to remember the theories once you have to see. The first one is Galileo Galilei. Galileo Galilei 1632, he gave the principle of Galilean invariance. Principle of Galilean invariance. He wrote one book, The Dialogue Concerning the Two Chief World Systems, Basic Principle of Relativity. He introduced the basic principle of relativity. Who introduced the basic principle of relativity? Galileo Galilei. When he introduced 1632. After Newton came 1687, Newton 1687, he wrote one book, Philosophia Naturalis Principia Mathematica. Philosophia Naturalis Principia Mathematica. Philosophia Naturalis Principia Mathematica. There he discussed about the Newton laws. He discussed about Newton laws. In which book? This book is very important. Philosophia Naturalis Principia Mathematica. Philosophia Naturalis Principia Mathematica. Now the third one is James Clerk Maxwell 1865, a dynamical theory of electromagnetic field theory he gave. The fourth one is Albert A. Michelson, Edward William Morley experiment 1887 to measure the motion of the earth relative to the ether, right. So next fifth one is Hedrick Antoine Lorentz. Hedrick Antoine Lorentz 1904 Lorentz transformation is given. By using the Lorentz transformation, Albert Einstein in 1905 he invented the special theory of relativity. Again he invented Albert Einstein in 1915 a general relativity or theory of gravitation he invented. So these are the inventions chronological order. So you have to remember first Galileo Galilei in 1632, later Newton 1687, Philosophia Naturalis Principia Mathematica invented, James Clerk Maxwell 1865, Albert A. Michelson Edward Williams Morley experiment he did 1887 to measure the motion of the earth relative to the luminiferous ether or ether. You have to remember luminiferous ether or ether. So that is the material. Ether is a massless and transparent material. That properties also I gave in the previous slides in go through. Albert Einstein in 1905, Lorentz in 1904, Albert Einstein in 1915 also gave the theory of gravitation. So these are the persons, Galileo and Newton and James Maxwell and Michelson and Morley. You have to take it as a which one, Lorentz and Einstein is there. Some questions you have to see. An inertial frame is one which, the inertial frame means that is the inertia law of Newton's first law of motion. We also call it as a inertia. All laws also motion, but Newton's first law is very very important. That is the inertia of motion is. Next you have to see one of the following quantities pick out that invariant under the Galilean transformation. Suppose you have to see the displacement x dash is equal to x minus vt, it is a variant. X dash is equal to x minus vt is a variant. Velocity u dash is equal to u minus v, it is also variant. Velocity, so u minus variant. The force F is equal to ma, F is equal to ma, m dash a dash is equal to m into a, which is invariant, it is invariant. The momentum v is equal to m into v, so m into v dash is equal to, v dash is equal to what we have to write here, v dash is equal to, we have to take it as a m into v dash is equal to m into, so v minus v minus ut, u minus v we have to take, so therefore, so it is not equal to this, so it's not equal, so because m v dash is equal to m v we have to get, we are not getting, so that's why it is a variant. It is a variant. Which is invariant? The force is invariant coordinate, because mass is invariant, acceleration is invariant, the rate product also you are getting the invariant. Clear? Now Michelson-Morley experiment proves the speed of light in vacuum is the same all the frame of reference which are related to motion. Because of the Michelson-Morley experiment only we got this statement. This statement A is correct. Now once again you have to see Michelson-Morley experiment proven in the presence of ether medium. Option B is correct. In the presence of ether medium, the Michelson-Morley experiment is did. The Michelson-Morley experiment was performed to measure the speed of earth relative to other, the speed of earth relative to ether, the speed of earth relative to ether. So that is very very important. Michelson-Morley experiment was performed to measure the speed of earth relative to the ether. Clear? So this is the class. So maybe tomorrow onwards regularly I have to teach the classical mechanics classes. So please you have to concentrate the classical mechanics and you enhance in the knowledge in the classical mechanics. Thank you.